Okay, let's take a look at this. Calculating energy transfer. Calculate the energy transfer in a wall section measuring 2 meters by 1 meter by 0.04 meters thick. So, what do we have? We have like 2 meters by 1 meter and then 0.04 meters thick with a thermal conductivity of 0.1. 0.1 joules. Oh, I see. This thermal conductivity is watts per meters times the degree Celsius, but watts is joules per second. So that's joules seconds, meters times degrees Celsius. So, okay, thermal conductivity. All right. Opposing sides of the wall section have a temperature of 10 degrees Celsius and 5 degrees Celsius after 1 hour. What are we supposed to be doing? Calculate the energy transfer in the wall section. Okay. Just to remind you, we have these formulas that we can use. So here we're trying to calculate the energy transfer. So maybe which formula are we going to use, huh? Energy. The energy transfer, that's going to be that's going to be Q, our Q. It's going to be in joules. All right, that's a hint. Well, let's just go about this like this. What's the first step? I'm going to list all the things that I know, and I know calculate the energy transfer of the wall, measuring 2 by 1. I know the area. I know the area of the wall. That corresponds to the A, right? Area of thermal conductivity. That's the area. So that is A is 2 meters by 1 meter. So that's just 2 meters squared. They tell me that the thermal conductivity of this wall is 0.1. So what is thermal conductivity? Thermal conductivity is K. So I'll have K equals 0.1 joules per second times meters times degrees Celsius. Ooh, that's complicated. All right, so 0.1, maybe I'll do 0.1. All right. Now I'm looking over here. I do have a difference in temperature, right? Difference in temperature. It says the temperature on one side of the wall is 10, and then on the other side of the wall is 5. An opposing side of the wall have a temperature of 10 and 5. Opposing sides, I forgot what I was saying. I paused it because there was a commercial on the music. Opposing sides of the wall section have a temperature of 10 degrees Celsius and 5 degrees Celsius after 1 hour. So the temperature difference, delta T, that's going to be, well, 10 minus 5 is just 5 degrees Celsius. So that's very nice. What else do we know? Is that all we know? I think that's all we know. Actually, let's see. So we have, well, the rate of energy transfer. I don't think we have that. Energy transfer, that's what we're trying to find, right? It says calculate the energy transfer. So that's what I'm trying to find. I'm trying to find Q. Change in time. Oh, I do have the change in time, don't I? Isn't there a change in time? After 1 hour? Okay. So maybe delta lowercase t, that's going to be, well, I think you have to do the change in seconds. So 1 hour is the same thing as 3,600 seconds. It has to be in seconds. And then, yeah, it tells you it has to be in seconds. What else? Area of thermal conductivity, we have that. Ooh, thickness of the material. We have that too. L. Okay. L equals, what was it? 0.04 meters. Was it supposed to be in meters? Thickness, we'll see. Okay. All right. And in this problem, I think we're going to have to do a couple of steps. So we want Q. We want Q. So what are equations that involve Q? Well, that one. But that involves P. If I take this, P equals Q divided by delta T, and I solve for Q by multiplying both sides by delta T, then I get Q, right, that cancels out, Q equals P times delta T. right? However, P is the same thing as all this stuff. So and this is all those things are what I have. So I'm assuming I need to use those. So P is the same as K times A times delta T divided by L. So then we have this formula. Now that's kind of crazy. That's kind of weird to use, but I mean you'll notice when you have to do something like that, just because otherwise you can't do anything. So let's calculate the energy transfer if we're using this formula. So Q then equals K. What's K? K is 0.1, right? 0.1 joules. Remember, put your units in. Some people didn't do that. Joules per meter, or joules times meter, well, whatever, degrees Celsius. And then that's in the top, times A. What was A? A was the 2 meters squared. So times 2 meters squared. One of those cancels out with that. That's nice. And then times delta T, capital T, that was 5 degrees Celsius. So times 5 degrees Celsius. That'll cancel out there. Oh, nice. We have joules per second. That's in watts now. And then we got to multiply by the change in time, which was 3,600 seconds times 3,600 seconds. And that will cancel out. Very nice, very nice. So we're left with just joules, except for we're also dividing by, we're also dividing by L. What was L? What did L say? Thickness of the material, and the thickness of the material was 0.4 meters. So this is 0.4 meters. Oh, and that cancels out with the other one. There we go. Now we're just left with joules. Okay, so Q equals, I'm going to put this in my calculator. And I get 9,000. 9,000 joules. Well, that's very nice. 9,000 joules. That's pretty good. Okay, that's a long video for one stupid example. Okay, so the energy that was transferred through the wall was 9,000 joules. Okay. Wait, no, it's 0.04. That makes it 90,000 joules. Just kidding. I was just kidding. I messed up. Sorry. There you go. There, 90,000 joules. That's a lot more. That's a lot more.